Pick a card, any card. You have a 4 in 52 chance of choosing an ace. Do you think you can do it? Wow. Now there are only 3 aces left. You have a 3 in 51 chance of choosing an ace. Do you still think you can do it? Amazing. You're good, but you've changed the odds again. You have a 2 in 50 chance. Pretty unlikely, but go ahead. Take your pick. Incredible. Right, this time if you choose an ace, I think I'll eat the rest of the pack. But don't be overconfident now. You only have a 1 in 49 chance. Stupendous. I'll tell you what, I'll give you one final go. What? What's the matter? Oh, I see. Scared of a none in 48 chance, are we? What? Eh? Oh, wait a minute, come on. I was only joking. You don't really expect me to eat them.
Actually, the probability of picking 4 aces is extremely unlikely, much more unlikely than he suggests. We must consider the joint probability of picking 4 aces from the pack. Multiplying the individual probabilities together gives a 1 in 270,725 chance of picking 4 aces in a row. Probability is a well-known factor. If you roll a dice, there's a 1 in 6 chance of a 4 coming up. If you buy a ticket for the lottery, you've got a 1 in 13,983,816 chance of picking the 6 winning numbers. So how do probability, chance and uncertainty fit into the world of computing? Predictive text isn't that different from pulling a card from a pack. It uses the letter already typed and models what is most likely to follow. A Q will almost always need to be followed by a U. That's pretty obvious. Using another example, INSI could be the start of insidious. But predictive text is likely to decide that inside is the more probable word.
It's conditional probability, you know.
Pardon?
It's the chance of Z given that X and Y have already happened.
Right.
Conditional probability is also behind Google's Did You Mean function. Type in a word slightly wrong or unusual, and the search engine likes to double-check for you. If you type BLOH, it finds the closest words, blob, blot, blow, and blog, for example. It then considers how often each word crops up on the internet. Google also builds an error model that works a bit like predictive text. This accepts the chance that the user made a particular mistake. By matching the closest words with the error model, Google offers the spelling that is most likely to be correct. In this case, the word is blog. We all suffer from spam emails, and spam filter technology has to continually evolve to keep level with the spammers. The filters themselves are based on probability.
Well, suppose, for example, you wish to filter out spam messages connected with mortgage sales. What these systems might do is go through the message word by word and look for the occurrence of words like mortgage or interest rate or repayment, and every time it saw a word of that nature, it would accrue a little more probability that the message was suspect. Of course, one word on its own isn't sufficient. The word mortgage might well appear in perfectly valid messages elsewhere. But at the end of going through word by word, it's possible for these systems to accrue really quite reliable judgments whether overall the message is suspect or not. And that's Bayesian reasoning. This is a sequence of conditional probabilities. Of course, what you don't want to have to do yourself is to nominate what these sensitive words might be. That would be very tiresome and it might not be very accurate at all. So one of the clever parts of these filters is that they're able to take a pile of spam messages and a pile of perfectly valid messages and work out for themselves on which words to base these quite subtle judgments.
The fundamentals behind chance and uncertainty certainly have their place in computing that many people use on a daily basis. But what other areas benefit from it? Perhaps somewhat surprisingly, the medical world is making strides using predictive techniques. One such area is predicting protein function, in order to understand what proteins do and to help with drug discovery. As an example, proteins in the BCL family play a role in tumour growth, and recently small molecule inhibitors of these proteins have been discovered, providing a key target for leukemia drugs. In this animation, the ball and stick structures are the small molecules that bind to the larger protein. Predictive techniques can help to identify binding sites, like those shown. Using probabilistic computational approaches, likely binding sites may be identified more quickly. Advances in understanding biology rely upon new software and tools. The people developing these need to know their maths. Dr. Chris Needham at the University of Leeds works on predicting protein function and understanding biological pathways and networks.
We can use computational methods for biological sequence analysis, structural similarity of proteins, and comparison of gene expression levels. Using information about proteins of known function, we can make predictions about other proteins. And we're able to quantify our uncertainty in the predictions we make by using probability.
To help make a difference in the world, by working in an area like protein function research, computer skills have to be supported by mathematical knowledge. In fact, an understanding of the maths behind computing will open up more challenging and rewarding careers opportunities.
Pick a card, any card. Oh, pick another. Good choice.